Hello everyone, Mr. Minnick's my name, math is my game. This morning I'm joined by a very special group of young women and young men. This is the 754 Mr. Minnick with the first period Algebra 2 crew. And today we're kind of going a little bit out of the not off topic definitely, because we need to talk about these things. Exponent rules. These show up in the Algebra 2 textbook somewhere in between Chapter 5 and Chapter 6. If you understand what Chapter 6 is all about, you'd know why they show up there. So anyway, exponent rules is what we're talking about today. I would urge you to take notes. You've probably seen some of these things all the way going back to 5th, 6th grade. There's going to be one that might surprise you today. So for all these exponent rules, we're going to say, let's let x and y be any real number. So the importance of setting this up is I'm going to use the variables x and y throughout all these exponent rules. And a lot of times when teachers go over stuff, they leave out important things, and I don't want to leave out anything important here. But x could be any real number, y could be any real number, and also m and n are natural numbers. M and n are natural numbers. Okay, so I'm going to be using x and y for a base, and I'm going to be using m and n for an exponent or for exponents. So I want you to keep in mind that the exponents that I'm using are going to be natural numbers. So we probably better take just a quick second and look at the set of natural numbers, just so everybody knows what we're talking about. The set of natural numbers looks like this. Anybody know the first element in that set? Not 0, 1. Remember, the natural numbers are also called the counting numbers. Remember the first week of school when I talked about your little 3-year-old nieces, nephews, siblings? I love hearing them count because they say, 1, and then they look at their fingers and hold up 2 fingers. 2, and then they hold up 3 fingers. 3, 4. They're so proud of themselves. They should be. All right, so keep in mind the exponents we're looking at are going to be natural numbers. Everybody all right so far? I know we're off to a slow start, so let's get right to it. The names of these, I couldn't care less if you know the names, and when I say that, I'm being truthful. The names are not important. What is important is that you understand how to apply those. So in the first instance, we're going to have similar bases, x to the m and x to the n, okay? So this is what happens when the bases are alike and you are multiplying. My 9th grade algebra teacher taught me this one. If the bases are alike, if the bases are alike, which they are, x and x, if the bases are alike and you are multiplying, bless you to everyone who's sneezing, and you're multiplying, that's you or me, you write the base. In other words, the base stays the same. So x to the m times x to the n, the base is going to stay the same. And anybody remember what you do with the exponents here? Add them, good. And you add the exponents. So x to the m times x to the n can be thought of then as x to the m plus n. And this is called, what's it called? The names are so confusing. The product of powers rule, I believe. The product of powers rule. The product of powers rule says if you have a base to some power times a base to another power, it's the base to the sum of those powers. So a specific instance of this might be something like x squared times x cubed. So according to the rule, it's going to be x to the 2 plus 3 or x to the 5th. The nice thing about using specific examples like that is it makes it real clear as to why things happen. Anybody remember that one video I showed a while back on polynomials? It was very poorly acted, and the one guy said, "Need a hand? Expand." So what we can do is we can look at x squared and say, well, that's x times x, and we can look at x cubed and say that that's x times x times x. And if we do that, it's pretty clear that we get x to the 5th. Everybody good so far? Again, I couldn't care less that you memorize the names of the rules. In other words, the names are insignificant, but it is imperative that you understand how they work. Okay. Going back here for just 1 minute, I should probably also say that in this, I'm going to use x and y throughout. Also, y cannot equal 0. Y cannot equal 0. Whenever we have a situation with a fraction, I'm going to be putting y in the denominator, and we know what happens when you divide by 0, right? That's where Siri tells you that you have no friends and all that. Yeah. So the next one then, let's look at the quotient of powers rule. It's kind of weird to go in this order, but that's okay. So let's look at the quotient of powers rule. The quotient of powers rule. It's just like the product of powers rule. Well, not just like it, but it's similar to it. So if we had something like x to the m divided by x to the m divided by x to the n. And I probably should have said that x can't equal 0 either. I'm sorry. X can't equal 0, y can't equal 0. Sorry about that. So if I have x to the m divided by x to the n, so in other words, if the bases are alike, if the bases are alike, and you or me are dividing, if the bases are alike and you're dividing, the bases are x, same bases, and you're dividing, whoa, not did I write diving? Wishful thinking. Dividing, if the bases are alike and you're diving, and you're dividing, you write the base, and do what with the exponents? Anybody recall? Bless you. And subtract, good, and subtract the exponents. Okay, so then this is going to equal x to the m, take away n. We'll probably come back to this because we need a little bit more information to go more in detail with this. The example we'll look at, we're going to assume that the numerator has a higher exponent than the denominator. We'll assume m's bigger than n for now. So a specific case might be something like x cubed divided by x squared. According to the rule, this is going to be x to the 3 minus 2. X to the 3 minus 2, or x to the first, or just x. Okay. So, again, back to that video. Need a hand? Expand. If you expand this out, we would see the numerator has an x times an x times an x in it. The denominator would have an x and an x. For those of you that missed last week, in 8.4, we factored and canceled, and what we see here is 2 of these x's will cancel 2 more, and it's pretty clear now to see what's left, right? So far, so good? We got 2 down and a lot more to go. There's a couple that I'm just going to throw out there. I don't know if this has a name, but x to the first power is just x. If I had to give that a name, I'd probably call it the identity power rule, the power of 1 rule. Maybe the implicit exponent rule. The implicit exponent rule. If there isn't an exponent, it's implicitly 1. Maybe the implicit identity exponent rule. You know, varsity math, if something's raised to the first power, we don't need to put its exponent. So I think everybody's good with that one, huh? Okay. How about this next one, the zero exponent rule? The zero exponent rule. It's a good thing earlier that I said x can't equal 0. So if we had x to the 0, and again, keep in mind, x is not allowed to equal 0. Don't even ask me why, but x can't equal 0. X to the 0, anybody know what this equals? It's 1. Does anybody know why it's 1? Has anyone ever asked their 5th, 6th, 7th, 8th, 9th, 10th grade teacher why it's 1? Because that's the way it is. Because that's the way, I like. Let's back that thing up for a minute. Let's go back. So far, what we've seen is enough to answer this question. What we've seen so far is enough to answer this question. X and Y have to be any real number. M and N are natural numbers. Ooh, but this isn't a natural power. Ooh. But we have seen enough information to make this work. You see this one, right? Everybody with me? Okay. So how could we make it so that we end up with x to the 0? Well, maybe we have something like x to the m over m. What would that be? That would be x to the m minus m. And what's m minus m? 0. Now we said x to the 0 is 1. Can you see now? I wrote this wrong. That's my bad. This is x to the m over x to the m. Do you see now why this works? What are you dividing when you raise something to the 0 power? You're dividing something by itself. And if you divide any non-zero real number by itself, what do you get? 1. That's why exponentiating anything to the 0 power is 1. How are we feeling? Good? So that would be a good essay question. Explain why the 0 exponent rule works. Because you are dividing something by itself. So I always ask the question, are there any questions, comments, concerns, short debates, or long debates? And I've made it clear that x is not allowed to equal 0. In case you're wondering, that kind of looks like an owl to me. Doesn't it look a little bit like an owl to you? By the way, I've got a couple knock-knock jokes. Knock-knock. Owls. Oh, I know. Yeah, so 0 raised to the 0th power is one of those questions that mathematicians have, I don't know if I've told you this or not, but mathematicians have debated this for 1,500 years and are still debating this. Let's think about it. 0 to the 0 power means we're dividing 0 by itself, right? There's several different ways we can consider that. We're dividing something by 0. If we divide something by 0, what do we know that is? If we divide by 0, what do we know that is? Thank you, it's undefined. So from that perspective, we would say that the right answer is that the answer is undefined. But so if we look at this from another perspective, if we look at this from saying, well, it's 0 divided by something, what's 0 divided by something? 0. So some math people make the argument, well, 0 divided by 0 should equal 0 because you're dividing 0 by something. And then other people say, hey, wait a minute, Mr. Postman, slow your roll. You're dividing something by itself. What's something divided by itself equal? 1. So people have argued for 1,500 years that 0 divided by 0 is undefined. That 0 divided by 0 is 0. That 0 divided by 0 is 1. They're all right, sometimes, in some way. This is one of those conundrums in math. This is one of those cans of worms that you just don't want to open. I could spend the rest of the school year talking about how to analyze this, but we're not. We're not going to. All right, so we got the 0 exponent rule, we got the implicit identity exponent rule, we got the quotient of powers and the product of powers. So far, so good? All right, we got a long way to go. How many exponent rules are there? Well, the next one is very alliterative. Sally sells seashells by the seashore. That's alliteration, right? And it's a tongue twister because sometimes alliteration is tough. Anyway, the power of a power. This is called the power of a power. So this is if we had something like x to the m to the n. And it's alliterative because the power of a power is the product of the powers. The power of the power is the product of the powers. So in this case, if we're raising a power to a power, we take the exponents and do what with them? Multiply, because that's what the product means. So a specific instance might be x to the squared to the cubed. Need a hand? Expand. Well, if we just follow the rule says it's x to the 2 times 3 or x to the 6th, because we would have x squared times x squared times x squared, or x times x times x times x times x times x, or x, 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 and then it's pretty clear to see that it's x to the 6th. Right? Questions, comments, concerns? The next two are kind of like cousins. Suppose we had something like x, y to the m. So this is the power of a product. Originally we had the product of powers, and then we just saw the power of a power. Well, this is the power of a product rule. The power of a product. The power of a product. So x times y to the m. Anybody remember how this one works? It's similar to the distributive property. What I mean by that is that the x gets the power of m, and so does the y. Okay? Keep in mind that this is true for a product. So again, with a specific example, maybe we have 2 times 5, the quantity, to the 3rd power. According to this would be 2 cubed times 5 cubed. And it would be okay to leave it like that. Okay. If you're not sure why, need a hand, expand. It's 2 times 5 times 2 times 5 times 2 times 5. That's a times. If we drop the parentheses, we would have 2 times 5 times 2 times 5 times 2 times 5. By the commutative property of multiplication, we'd have 2 times 2 times 2 times 5 times 5 times 5. Make sense so far? Good. So the next one is the power of a quotient. 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 So I told you these are cousins. So we have a quotient, x divided by y to the power m. And again, this one's kind of like the distributive property. We're going to have x to the m divided by y to the m. This is one of a lot of people forget about. They drop the ball on this one. So a specific instance is if we have to square something like 4/5. 4/5 the quantity squared. According to the rule, what we need to do is take 4 and square it and take 5 and square it. Okay? If you're not sure why, well, it's like we have 4/5 times 4/5. And if we drop the parentheses, we have 4 times 4 over 5 times 5. Okay? So that one's oftentimes overlooked, especially when people have to square a fraction or cube a fraction. How we doing? Getting it? So we're going to take a minute now and talk about the earth. The earth. So suppose that's the earth. And this is you. Now you're not that big. You think you are, but you're not. So what keeps you grounded to the earth is this attractional force, right? Because the earth is much larger. Did you know that if you stand next to a train, that gravity is attracting the mass of the train has an attractive force to you, to the train? It's not that much. It's probably nothing that we could measure with most instruments, but there is an attractional gravitational force between you and a train. Can you believe that? But the earth is very big, so the earth attracts you to it, right? And that's why you can't jump and fly to the moon, because of gravity. Everybody get that? There's a reason that I mentioned this, and it has to do with simplifying something like this. X to the 8th divided by x to the 12th. Okay? What's bigger, 12 or 8? 12. So if you think about gravitational force, then our x's are going to be gravitated toward whatever one is larger, or they should be. So would things tend to gravitate toward the numerator or denominator of this expression? The denominator. Does that make sense? This is going to set up our next rule. Okay? So what ends up happening is you saw that rule. This is going to be x to the 8 minus 12. Everybody with me? So that's going to end up being x to the negative 4th. But if you understand gravity, you'll realize, 12's bigger than 8. So what this means is everything should kind of gravitate toward the bottom. So in the bottom, we should have x to the 12 minus 8. And what has to hold the place up top? A 1. Good. So what ends up happening in this scenario, in this situation, is we end up with 1 divided by x to the 4th. Do you see what a negative exponent does to something? So here it is, the negative exponent rule. The negative exponent rule. The negative exponent rule. X to the power negative m. Remember, we assumed that m and n are natural numbers, and they are. So they're not negative, they're positive. This ends up being 1 divided by x to the positive m. So a specific instance would be if we had something like x to the negative third, that would be 1 divided by x to the positive third. Now it's kind of difficult to come up with a specific, for instance, of why this is. But I just did something similar to this a minute ago. Suppose we had something like x to the 6 minus 9. That would be something like x to the 6th divided by x to the 9th, wouldn't it? So if you expand that out, that's x divided by x. And if we think about that which cancels things out, these 6 are going to cancel out 3, 4, 5, 6 of those. Does this make sense? So what I want you to realize, and make special note of it, is this. Negative exponents. Negative exponents. Do not make quantities negative. Exclamation point. Negative exponents don't make numbers negative. A lot of people think that they do. They don't. If something's positive, by exponentiating it, there's no way to make it negative. I love the number 2, probably one of my favorite, top 5 favorite numbers. If we took the number 2 and tried to raise it to a bunch of different powers, if we raise 2 to the negative 2nd power, well, we get a 4th. If we raise 2 to the negative 100th power, well, we get a really tiny fraction. If we raise 2 to the 1/2 power, well, we get a little bit smaller number. The point is, you can't raise 2 to any power and make it negative. So be aware that negative exponents do not make quantities negative. Everybody go with that? All right, cool. Negative exponent rule part 2. Negative exponent rule part 2. Negative exponent rule part 2. Part 2, as they would say in, how do they say it in France? Duh, part 2. Okay, they don't eat omelets over there either, which is weird, but whatever. This says if we have x divided by y, the quantity to the negative m power, well, it puts x over y under 1, which does something weird. It ends up being 1 over x over y, which is 1 times y over x, which ends up being y over x. Anyway, let me just get straight to it. This flips the fraction. It flips a fraction. It's y over x to the positive m, which then in turn would be y to the m divided by x to the m. So know this. Know that a negative exponent flips an existing fraction over. I probably should have done this first. X over y to the negative 1 is y over x. I probably should have done that first. Okay. Know that a negative exponent will flip an existing fraction or invert an existing fraction. Okay. So if we already have a fraction, the negative exponent will flip the fraction over. How we doing? We're almost there. I think there's only like one more that we need to see. Pretty sure there's only one more that we need to see. Before we do, we probably ought to practice an example or 3. So example number 1, let's try to simplify this. 3x squared y cubed all over 15x to the 4th z, the quantity to the negative 2nd power. A couple different ways to proceed here. There's more than one way to do this. PEMDAS says let's work our way from the inside out, right? Can we do anything with the 3 and the 15? Can we do anything with the 3 and the 15? We can divide them both by 3, right? So that's going to make that a 1 and a 5. So there's going to be a 5 in the denominator. Now keep in mind, all this is going to be raised to the negative 2 power still. If we analyze the x's, what's going to end up happening with our x's? Let's think of that gravity thing. What's going to happen with the x's? Denominator, bless you, we're going to have what? X to the power 2 in the denominator, right? Everybody with me? Y cubed is in the numerator. There's nothing that can happen with that. Y cubed still in the numerator. What about the z in the denominator? It's still there. Can't do anything with that. So now we've got to realize, this is still being raised to the negative second power. So what are we going to do? The negative or the 2 first? The negative. If you put the negative in, then it's going to take the whole fraction and do what with it? It's going to flip the whole thing. So that which was in the numerator is going to go to the denominator. That which was in the denominator is going to go to the numerator. So we're now going to have 5 x squared z in the numerator and y cubed in the denominator. And this is where people mess this up. Now all this is still being raised to a power. Guess what power? To the positive 2. So now we go back to that rule then that's kind of like the distributive property. Everything in that quantity is going to get the second power. So we're going to end up with 5 squared in the numerator. We're going to have x squared, right? And we're going to have z squared. And in the denominator, we're going to have y cubed squared. I think this covers just about all of them. So what's going to end up happening then? Can we simplify that any further? That's going to be what? 25 x to the what? X to the 2 times 2, x to the 4, z to the what? Z to the second, all divided by y to the 6th. Good. How do we feel about that one, all right? Questions, comments, concerns, short debates, long debates? So last week, we saw something like this. Example 2. Simplify. X plus 2 times x plus 1 divided by x plus 2 times x plus 3. We saw something like this after we did some factoring. Would everybody agree that what we end up with here is x plus 2 to the 1 minus 1, or x plus 2 to the 0? And so that whole expression kind of turns into a 1. Does everybody kind of agree with that? So that's why this canceling works. You divide something by itself, it's just 1. That's why this canceling works, okay? So I probably should have done the exponent rules last week. So the answer here, in case you missed last week, the answer here is x plus 1 over x plus 3. That's it. That's it. Okay. Any questions? There's one exponent rule that doesn't exist, and then we'll look at the last one, and then that's it for the day. The non-rule. The non-rule. This is not a rule, but you're going to think it is. X plus y, the quantity to the m, is not x to the m plus y to the n. A lot of people think that it is. Let's just look at a real basic one. X plus y, the quantity squared. When we FOIL that, we get x plus y times x plus y, and we get x squared plus 2xy plus y squared, right? We used the binomial theorem to expand that. A lot of people want to make up this exponent rule, and it doesn't exist. It's not for real. Okay? That's not a rule. Don't think it is. And then we got one more. And then I got one more knock-knock joke. I hope everybody is learning something new out of these rules. Maybe you already knew all this. If you did, I'm sorry. But this is probably a new one to you. The rational exponent rules. Keep in mind, x is a real number, not equal to 0. Y is a real number, not equal to 0. M and N are natural numbers. X to the power 1 over M. I love this one. Oh no, that symbol. What's that symbol? That's the radical sign, right? Some people call it the square root sign. There's a number in that spot that's called the index. Okay, the number in that spot, just so you know, the number in there is called the index. Implicitly it's 2, but in this case it's going to be m. This is the mth root of x. There's another one that says if we have x to the m divided by n power, we're going to introduce this radical again. Guess what the index is going to be this time? The index this time in the red one here is going to be n. So we're going to have x, and the interesting thing is where the m goes. The m can go here, or we can write this as the nth root of x, all that to the m power. We're gonna be doing this in chapter 6. Okay. What you talk about, Willis? So sometimes you'll notice me writing the date on the board. I might write the date as 169 to the 1/2 power. What's that mean? It means we're taking the second root, or the square root of 169. What's that? 13. You don't believe me. 169 raised to the power 1/2. Isn't that the same thing as the square root of, yeah, as the square root of 1, yeah. What do you think? Huh? Convoluted? What's that mean? Unnecessarily complicated? So when we get to logarithms then, you're going to need to be able to evaluate something like 8 to the 4/3 power. Let's think about this. 8 to the first is 8, right? We're raising 8 to a power bigger than the number itself, so it's going to be, our answer is going to be a number bigger than 8. Anybody ever think like that? That's called number sense when you think about numbers. So this is going to be the 3rd root of 8 to the 4th. Now 8 to the 4th is a wicked huge number. So maybe I'm going to move that 4. Maybe I'm going to move that 4 out here instead. I do know the 3rd root of 8. It's 2. And 2 to the 4th would be 2 times 2 times 2 times 2, or 2 squared squared, or 16. Hey, 16 is bigger than 8. Of course it is, because we're exponentiating it to a power bigger than the number. What do you think? One last knock-knock joke after shout-outs. Shout out to my 2nd period class and my 6th period class. I hope you got something out of it. I hope you didn't fall asleep. Shout out to my 1st period class. Shout out to the future Mr. Minnick. Shout out to Miss Guy. Shout out to Mr. Lysak for having a snow day. And the final knock-knock joke. This is it. Knock-knock. Nobody.